Hi everyone, welcome to Physics 151, Lecture 15, Part A. This half lecture is just about one application of Newton's second law, specifically dynamics problems involving inclined planes or ramps of constant slope. I'll be doing examples from lecture tutorial 15A, and there are some inclined plane problems in Mastering Physics in homework 15. I'm going to start off with frictionless inclines, and then we'll cover inclines with friction, including friction. And I'm going to show you a derivation right now of basically, quote unquote, solving the problem. Everything we can find out about this inclined plane situation, just starting from first principles and trying to solve this like any other two-dimensional dynamics problem. I hope that you should be able to follow along because this is just like our other 2D dynamics problems. However, this whole derivation is just a little bit tricky and complex enough that I would not expect you to be able to do it on your own from memory, for example. All right, let's do this first by following the same steps as we have for all the other dynamics problems. Step 1, I'm going to define my axes. Step 2, create a free body diagram. Step 3, decompose my forces along those axes into x and y components. And then step 4, solve Newton's second law along each of those components. So as you can see, I've already laid out a lot of those 4 steps right here. So starting over again, step 1, let's define our axes. Now, in the past, we've almost always chosen our x-axis to be horizontal and our y-axis to be vertical, upward away from the center of the Earth. And that's because that tends to make our math simpler for things like freefall problems or projectile motion problems, where the force of gravity lies along the vertical direction. As you can see, that's true in this case as well. The weight of the object that's on the inclined plane here, it does have a weight that lies along the vertical axis. However, the normal force is not away from the center of the Earth, but is perpendicular to the surface of contact. So if you think back to our definition of normal force, the direction that it acts is always perpendicular to the surface that the object is touching, right? The surface of support. So if we were to choose our positive y direction to be vertically upward, that would actually be complicated because the normal force would not lie along the axis. But by choosing our y-axis to be like this, perpendicular away from the ramp, then the normal force lies exactly along the y direction, and it has no x component, and its y component is simply its entire magnitude. So that's actually a convenient thing that simplifies our math. The same goes for the x direction. For the x-axis here, we can see that our motion is going to be along the ramp, right? Whether the object is released from rest and slides down, or if we start by giving it some initial velocity up, then all of the acceleration and velocity and displacement of the object will be along the ramp in the so-called parallel direction. So if we choose our x-axis to be in the parallel direction, then that saves us a lot of time and makes our math simple as well. We could choose the positive x direction to be uphill. However, our textbook, Young and Adams, prefers to choose it downhill most of the time, because for most of these inclined plane problems, the motion will be largely in the downhill direction. So that way it just gives us more positive quantities and fewer negative quantities. However, that's fine. If you choose the positive x direction to be uphill, that's okay too. You just have to remember and stick with it for your entire problem. So what we find then is most of our quantities are going to have only an x component or only a y component, and we've made our overall math simpler by choosing our axes to be perpendicular and parallel. And there are many textbooks that actually call this the so-called perpendicular direction and parallel direction, like that. However, I'm going to follow Young's Young and Adams convention, which is to call those the x and y directions. But be prepared to see these other unusual symbols, perpendicular and parallel, if you look at certain textbooks or study guides or other resources. All right. So what that does is it leaves us with the fact that our weight here is the one big quantity that does not lie exactly along the x or the y axis. The weight is going to be the one force that we're going to have to decompose into an x and a y component. So how to do that is, well, we learned a long time ago that to find the x component of a vector, you take its full magnitude, which we know is going to be equal to mg, and then you multiply it by the cosine of the trig angle. Well, in this case, the trig angle starts in the positive x direction and goes through y around that direction. So it's going to be equal to 270 degrees plus the wedge angle of the incline. Well, it turns out if you take cosine of 270 plus alpha, it simplifies to just sine alpha. Another way to think about this is to say, well, instead of following our usual recipe for calculating the x and y components by using the trigonometric direction, this is one of those rare times where we're going to do it from scratch, and we're going to cook up our own recipe. And this is the way most textbooks do it. You note that this angle that appears right here in the triangle is exactly the same as that angle. And there are a number of ways you can show that geometrically, but the easiest way is just to think about it in a common sense manner. If the ramp gets more and more shallow, you can see how this angle here would get, how the weight would get closer and closer to the y direction, and that angle would shrink. And if the ramp got steeper and steeper, you can see how this angle here would grow bigger and bigger. In that case, you can see that the x component here is opposite, and the full weight, mg, is the hypotenuse, and therefore the sine of alpha must be opposite over hypotenuse. So opposite over hypotenuse is that. Therefore, the x component must be mg sine alpha. So that's how we get the x component of the weight. You can go through a similar argument for the y component of the weight right here, using this little triangle, or using our definition of the trig angle. And when you're all said and done, you get negative mg cosine alpha. And the negative sign comes from the fact, of course, that it's pointing in the negative y direction. So when you're all said and done, you wind up with these as the x and y components for the weight, where x and y, once again, are defined along these two perpendicular and parallel directions. We can see by inspection very quickly that the x and y components of the normal force are just 0 for the x direction and positive full magnitude for the y direction. All right, so we've done our first 3 steps now, although I guess I took them slightly out of order. But the first 3 steps were choose our axes, create a free body diagram that inventories all of the external forces acting on the mass, and that in this case that was just weight and normal force, and then decompose those two forces along our x and y components as defined in our axes over here. So that's what we have now, x and y components for each of those forces. So now we're ready to proceed to Newton's second law. So Newton's second law says, okay, if we take the sum of all of the x components of all the forces, that should give us mass times x component of acceleration. And then later I'm going to come down here to the y components and do exactly the same analysis. Let's see what we can learn first from the x components. So if I take the x components of the two forces, that's 0 plus mg sine alpha. So that's the x component of the normal force plus the x component of the weight. And the right-hand side stays the same. Wow, all right, well, it looks like first, the mass is going to cancel. And second, I'm going to learn that the acceleration x component is equal to g times sine alpha, right? I can see at a glance, because I know that sine alpha is a positive quantity and g is a positive quantity, I can see at a glance that this is positive, and the positive x direction, remember in this case, is downhill. And of course, that makes total sense. We would expect the acceleration of a block released on a frictionless incline, we'd expect it to just accelerate down the hill. If you released it, well, all right, we don't know the initial velocity of this object. So I should correct myself there. Okay, we don't know whether v naught is downhill or uphill. But what we do know is the overall acceleration of this object will be in the downhill direction. So if it is starting from rest or initially moving downhill, it will speed up. And if it's initially moving uphill, it's going to first slow down, briefly come to rest, turn around, and then start speeding up in the downhill direction. So the acceleration will be in the downhill direction either way. Let's do the analysis for the y components now. If I add up the y components of the two vectors, I get the full magnitude of the normal force for the y component of the normal force, and then I get negative mg cosine alpha for the y component of the weight. Finally, we know that in the y direction, there is no motion at all. Remember, the y component is perpendicular to the incline. This object, unless the object flies off of the incline or sinks into the incline, neither of which is happening here, nor is it physically possible in our sort of idealized classical case, there is no motion at all in the y direction. No displacement, no velocity over time, and therefore no acceleration either. So in other words, the fact that the object stays on the ramp means that the y component of acceleration must be 0. And what we learned from this, therefore, is that the normal force turns out to be equal to mg cosine alpha. All right, we know that the direction of the normal force is perpendicular away in the sort of upward-ish direction. So we know that that's the direction of the normal force, perpendicular to the incline, and this is the magnitude of the normal force. So we're able to solve for that out of the y component direction. Great. So we've completely now solved this situation for the motion of an object on a frictionless incline of constant slope. So on the next slide, I just have this written up in a slightly neater way. And one more thing to observe about this expression for the acceleration is the fact that, first of all, as long as the inclination of the ramp remains constant, the slope of the ramp remains everywhere constant at angle alpha, then the acceleration is constant. Okay? So that's great. That means we can use our equations of kinematics for constant acceleration, like v equals v naught plus at, or v squared equals v naught squared plus 2a delta x. We can use those in the x direction because the acceleration has one constant value at all times. The other thing to notice is this does not depend on the mass of the object. So if we had a bunch of objects all with different masses, on the same incline with angle alpha on the same planet with acceleration g, then they'll all have the exact same downhill acceleration. This sort of agrees, initially, this seems remarkable, that if we had a whole bunch of objects and we release them of different masses and we release them all from rest, that they should all then accelerate down the incline at the same acceleration. But if we consider the fact that we know this is already true for free fall, right? Galileo already discovered that this was true and asserted this was true for objects that were simply falling straight down. Well, free fall straight down through space is just the equivalent of an angle alpha that's equal to 90. So when alpha goes to 90 degrees, which would be an incline that's so steep, it's basically a vertical wall, and we just drop some objects and they all descend like this next to the wall. Sine of 90 degrees is just equal to 1. So then what does the acceleration become? the acceleration becomes just g in the downhill direction, which is exactly what it was for free fall, remembering that the positive x direction is downhill. So in this case, that would be, if the acceleration x component were positive g, that would be the downhill direction. Great, then that's excellent. That means that this makes sense. It agrees with what we would expect for the limiting case of an incline that's so steep it's exactly vertical. Then what do we get? We get the acceleration of an object in free fall. At the same time, we find that the normal force would go to 0 because this wall is no longer exerting any normal force on these objects as they simply free fall next to it. Finally, if the ramp were to become so shallow that it were flat, then we would find that the angle alpha would go to 0, sine of 0 goes to 0, and the acceleration would just go to 0, which is what we would expect for a perfectly level table. And in that case, the cosine of 0 degrees is 1, and the normal force just approaches mg, which is what we would expect for that same situation. Let's now consider the case of an incline with some friction. So in this case now, compare this briefly. I'm going to flip back and forth between this situation here where we've added friction, which is just one more force vector, compared to the previous slide where there was no friction. Everything else is still the same. So notice how the normal force here does not change. And if we leave the axes the same, then the normal force components will be exactly the same as well. The weight doesn't change. So if we leave the axes, x and y axes alone, then the weight components don't change either. The only thing that's new is the addition of this friction vector right here. So if we start over again with our steps, choose our axes, free body diagram to inventory all the forces, now there's a third force that we've added to that inventory, which is kinetic friction in the case of an object that's already in motion. And if we assume that that motion is downhill, which is important, then we can draw the kinetic friction in the uphill direction. Okay, and before we leave this example, we'll revisit that briefly for the reverse, in case the object happened to have been moving uphill to start. In that case now, all we do is we add one more vector, and we can decompose that friction, that kinetic friction vector, into its x and y components. We can decompose it simply by inspection. We look at the kinetic friction vector, we can see that the entire magnitude points in the negative x direction. So therefore, we take the whole magnitude of kinetic friction, which we know is equal to mu k times normal force, and we simply point it in the negative x direction, and that's it. That's the x component, and the y component is 0. We can see by inspection there is no y component. It points only in the negative x direction. What would happen if instead the object were sliding uphill? So in that case, if the object, let me choose a slightly different color. If the object were uphill, how would my free body diagram change? In that case, my free body diagram, normal force would be unaffected, weight would be unaffected, but this kinetic friction force would now be in the downhill direction. Okay? So now, when we go to write what the kinetic friction is in its two components, the only difference now is going to be that the whole magnitude of the kinetic friction would simply be in the positive direction, which would be downhill. That's all. So if the object, let me summarize that again. If the object happened to be sliding or moving in the uphill direction, so if the velocity is uphill, then the kinetic friction would arise in the downhill direction, and therefore its x component would be positive instead for the downhill direction, instead of negative, which is the uphill direction, for the x component of the friction force. Okay. All right, so that's how I would change my my free body diagram and therefore my components of my forces if the object happened to be sliding uphill. That's really interesting. That means that everything we're going to do with Newton's second law in the x direction, it would be a little different if the object were sliding uphill then downhill. So I'll revisit that one more time before we leave this example. All right, so now just to clean things up a little bit, I'm just going to clear my writing, and let's do the same analysis as we did before for Newton's second law along the x and y directions. So first, in the x components, let's take the x components of all three of our vectors now. 0, I should just say x component of normal force plus x component of weight plus x component now of friction. So I have 0 plus mg sine alpha plus negative mu times normal force equals mass times x component of acceleration. Now, in order to proceed, I'm at a little bit of a stop right now because in order for me to solve for this acceleration over here, I need to first figure out what that normal force is equal to. Okay. Now, I kind of already have a hunch. I know what the answer is going to be, but the normal force magnitude lives in the y direction. So let's put our x components on pause and jump down to the y components and try and solve those first. Okay, so now let's add all the y components of all of these three forces, and I get y component of normal force, y component of weight, and y component of friction. And finally, we know that the acceleration in the y direction is 0 because, like I said, the mass stays on the surface. It doesn't rise above the surface or sink down into the surface. So in the y direction, there's no motion ever. So what we get from this, we get the same result as we did for the frictionless case. Right? So the normal force in this case with friction is the same as it was without friction. Now I can use that up above, and I can proceed with what I was doing for the x components. So now let's keep going with the x components. Mu, and now I'll plug in this value here for the normal force. All right, great. So it looks like I can simplify a little bit, and then I'll solve for the acceleration. So I see that there is a mass term everywhere, so I'm going to go ahead and cancel that out. And now I can go ahead and solve for the acceleration. And the acceleration is going to be equal to g sine alpha minus mu g cosine alpha. All right, let's think about this a little bit and see what the math is telling us. So first of all, in the case of no friction, like what if we explore what this becomes in the frictionless case? So in the frictionless case, we would expect mu to go to 0. As that happens, we're just left with acceleration is equal to g sine alpha. And sure enough, that matches the result we had on the previous slide. So in the frictional case, as mu gets smaller and smaller, the value of the acceleration approaches that of the frictionless case. Great. Second, let's consider what would happen if the object were moving uphill. If the object were moving uphill, we decided that this component right here was going to be positive instead of negative. So that means that this here ends up becoming a plus sign instead of a minus sign. Okay? That's really the only difference if the object were sliding uphill. Finally, let's consider whether this object is, I'm sorry, let me clear. Oh, I didn't mean to clear everything. I just want to clear a little bit. Finally, let's consider whether this acceleration is in the uphill direction or the downhill direction. Well, if the acceleration is positive, if this quantity here, whoops, that was a mistake. If this quantity here overall were positive, pardon me, if the acceleration overall were positive, then that would be the downhill direction. So that would happen when mu is small. When mu is small, then the second term is going to remain smaller than the first term. The first term will be bigger. In that case, you'll wind up with a positive value for the acceleration. And that's a downhill acceleration. So what that would mean is that even though there's some friction present, the object would still accelerate in the downhill direction. And if you released it from a slow speed, then it would, and if slow downhill speed, it would speed up in the downhill direction. And if you release it in the uphill direction, well, then this would be a plus sign here, but it would be slowing down because the acceleration is downhill. If, on the other hand, the friction were really, really strong, if we consider if mu was very large, whoops, I did not mean to erase that. If mu were really, really large, then we would wind up with a negative value here for the acceleration. And in that case, what would we find? That would be an uphill acceleration. So again, we're considering the case of an object that starts out moving downhill, so it has some downhill initial velocity, but the acceleration is in the uphill direction. So that means that the friction is so strong that it's causing the object to slow down. And eventually, after the object gets a little further down, it'll probably grind to a stop. Okay? So that would be in the case of a very strong, a very large coefficient of friction. If the coefficient of friction were weak, then the object would continue to accelerate in the downhill direction, just not very fast. All right, I'm going to clear all of this, and I have a nicer looking version of that right here. Oh, I forgot to say that that there's a limiting case in between the two things that I was just talking about, which would be when the amount of friction is just right, that this whole acceleration here goes to 0. And that would be true when the amount of friction is equal to tangent of alpha. And in that case, when acceleration is 0, then that means that the object is simply going to slide downhill at a constant speed. All right, let's look at a couple examples. I'm going to use problem 1 and problem 4. Problem 1 is a frictionless case, and problem 4 is a static friction case that we haven't really discussed yet. Problem 3 on the tutorial is actually just what we just did. It's asking to derive an expression for the normal force and the acceleration for an object that is on a frictional incline. So we just finished that. Okay, I'm going to switch to my desktop camera now, and we'll take a look at that. So here we are with tutorial 15A, and let's start with question 1, which is a frictionless incline. I actually start off asking you to make some predictions. Okay, based on what we know about just the directions of the forces here, or based on the fact that we've already derived these expressions for what these values should be: the normal force, the direction of the normal force, the magnitude of the normal force, and the acceleration, to make some predictions about what those are going to be. So I'm going to let you, if you'd like, you can pause the video and try and answer these questions right now as a brief review, and then resume the video as soon as you're done. Okay, now we know that the direction of the normal force is going to be perpendicular to the incline. Okay, that's always the direction of the normal force from any surface of contact. So it's perpendicular to the ramp and outward from the surface. So in other words, it's not perpendicular inward, it's perpendicular outward in the normal direction. The magnitude of the normal force, we've already derived the expression for it, is equal to mg times cosine alpha. So it's something less than m times g, because cosine alpha is always a value between 0 and 1. And that makes sense, right? We would know the normal force would be equal to mg only in the case of a horizontal level surface. And then as the ramp gets steeper and steeper, the value of the normal force is going to get weaker and weaker. And then finally, we know that the downhill value of the acceleration is g times sine alpha. And therefore, this is always less than g, because again, sine alpha is always a value between 0 and 1. And we know that. We know that for free fall, the acceleration will be exactly equal to g. And then for a ramp that's anything more shallow than a vertical wall, the acceleration is going to be something less than the full downward g. So we've already derived these values a few minutes ago in the lecture. And now let's just calculate what some of those values are going to be. So what's the acceleration of the mass down the incline if the mass is 5 kilograms and the incline has an angle of 25 degrees? So in that case, the acceleration is equal to g times sine alpha. This is 9.8 meters per second squared. And I asked my calculator what sine of 25 degrees is. And it turns out that that's about 0.4226. And that means that the acceleration has a downhill component. Remember that the x direction here points in the downhill direction parallel to the incline, and the y direction points perpendicular to the incline, is equal to about 4.14 meters per second squared. Now this looks like it's actually sort of a 2 sig fig value maybe-ish, so we can round to 2 sig figs, 4.1. The magnitude of the normal force we've already derived is equal to mg cosine alpha. So in that case, this is 5 kilograms, 9.8 meters per second squared, and cosine of 25 degrees. And I calculate what all that is, and that turns out to be about 44.41 newtons, which is about 44 newtons if I round to just 2 significant figures because of that mass right there. Now, if the block were released from rest at a vertical height of 2 meters, so not a distance along the ramp, but a vertical height of 2 meters, how much time will it take to reach the bottom of the ramp? All right, well, let's sort of think about the geometry here of what this is asking. So I'm releasing the block from a vertical height, which I'll call h, which is given as 2 meters. And then I want to know how long it's going to take to get to the bottom of the ramp. Well, what I know is the acceleration along the ramp, right? Because remember, this is the positive x direction. So displacements are along the ramp, x displacements along the ramp. Specifically, it'll be in the downhill direction. So if I'm given the vertical height h, first I need to solve for what that downhill displacement will be in this direction. And then second, I can then use our equations of kinematics with this acceleration to solve for the time. So first, let's find the downhill displacement. I can use SOHCAHTOA to decide that sine of alpha is equal to opposite over hypotenuse. So that allows me to solve for the hypotenuse. Two meters divided by sine of 25 degrees. And that's about 4.73 meters. Okay? I know this is going to be a 2 sig fig final answer, so I need to retain at least a third significant figure for now. All right, now, separately, now that we know the downhill displacement, we can then use our kinematics for constant acceleration. And I can choose one of my kinematics equations that will allow me to solve for the time. Well, I know the displacement. I want to find the time. I think I'll use equation number 2. Displacement in the x direction is equal to v naught x times t plus 1/2 a t squared. Now, solving for the time initially looks like a quadratic problem, but fortunately, our initial velocity is 0 because it's released from rest. So it looks like this is going to be 4.73 meters is equal to 0 plus 1/2. Again, positive x is the downhill direction. So I have a downhill acceleration, keeping my extra sig fig for now. And this is a positive displacement because it's a downhill displacement. And that allows me to solve for the time as 1.51 seconds. Now I can round to 2 sig figs for my final answer. Okay, let's now go to example question number 4, which doesn't have any numerical values, but this is just one more algebraic problem. And this is asking us to consider the case of static friction for an object that's on the incline. So the question is, if we want to know, we have an object of mass m on an incline of angle alpha, and we want to know how grippy does the incline need to be? What is the coefficient of friction, the minimum coefficient of friction needed to be able to keep the block at rest if we release it from rest on the incline? All right, so that means I think we should, this is a dynamics problem, although it's a statics problem, which is sort of a subclass, right, of dynamics problems. We should follow our steps that we would for any other dynamics problem. First, let's define our axes. I'm going to choose same sort of axes we had before. Positive x direction will be downhill, and then the positive y direction will be perpendicular upward away from the hill. Second, let's do a free body diagram of all the forces that are acting on the mass. So I see that there's a weight, and I know also that there is a normal force, and I know that there's going to be a static friction force as well. And if I wasn't sure which way I should draw it, which direction I should draw it, then we can wait just a moment and see what the net of the other forces is that is parallel to the surface. In other words, the x components. So let's do that first. So it looks like my weight is going to be decomposed into a y component and an x component. In other words, a perpendicular and a parallel component. This is the x component here, and that's the y component there. Right? Now I can see at a glance that the only force out of the weight and the normal force, the only one that has an x component is the weight right here. And the direction of that net force parallel to the surface is in the downhill direction. So I can then tell that the static friction must be acting in the uphill direction to try to keep the block from moving. So my static friction is going to be acting in the uphill direction. All right. So now I can express these, I can decompose these forces, step 3, decompose them along the axes. And I'll just write them out really fast. By inspection, I can see that the normal force has no x component, and its entire magnitude is in the y component direction. Static friction. Now, normally, we wouldn't know how large a static friction should be. It would be an unknown quantity, right? We would leave it as an unknown, and we just say, all right, F sub S, and it might be something that we might have to solve for if it's not given to us. But this particular problem is asking about the limiting case. It's saying, what's the minimum amount of grippiness that this ramp has to have so that the block will still remain at rest when we let go? Well, what that means is it means that the static friction, whose magnitude is always a value from 0 up to some maximum, okay, this is the max static friction, must be operating at its maximum value, must be acting in the case when this is the equality. In other words, let's consider the limiting case, as we like to call this. Right? So the x component here is going to be negative mu times normal force. And there is no y component if you look at it. So I'm just going to remind us that this is the maximum value because we're considering the limiting case. right? So we've reduced mu to the point where this, this friction needs to climb all the way up to the equality here so that it's just at that limiting case where if there was even a smidge less mu, then the object will break free. All right, so that's the sort of approach that we always use for these limiting case type problems. You take the equality, okay, the situation where this is exactly equal, and then finally we have the weight. And as we showed earlier in this lecture, you can show that the weight has an x component, a downhill x component of mg sine alpha, and a y component of negative mg cosine alpha. And again, I know it looks backwards with the sine alpha in the x position and the cosine alpha in the y position. But remember, alpha is not the trig direction. Okay, alpha is not the trigonometric direction, so this is fine, and you can prove it to yourself separately. All right, now finally we can apply Newton's second law to the x and the y directions and solve for the motion of the object. So let's do that. So we can apply Newton's second law to the x components and separately to the y components. If we start with the x components, we're probably going to hit that same dead end again about the normal force. Here, I'll show you what we mean. Let's add up the x components here of all three of the forces. And by the way, we want everything to remain at rest. So we can just set the acceleration equal to 0 because that block is not moving. It's a static case. All right. See, we have an unknown here, right here. So we can't solve for mu until we figure out what the normal force is first. So we'll come back to that. Let's put that on hold. Now let's look at the y components over here. So adding the y components of all three of the forces. And again, this is going to be 0. And in this case, it's not because it's at rest, it's because it always stays on the surface of the ramp. So there's never any y motion at all. So it's sort of rest. It's rest in the y direction, right? Okay, so in that case, now we can see that the normal force ends up being just equal to mg cosine alpha. Aha, so that's the same as it was for the frictionless case and for the other friction case we solved for as well. So now we can use that in this equation over here for the x components, and we'll plug that in and we'll see what we get. So we get that, you know what, I'm going to move this to the other side of the equation. So let me just do one step of algebra first. Okay. Now we'll plug the normal force in. We get mu times mg cosine alpha is equal to mg sine alpha. Now this is interesting. First of all, the mass and the gravitational acceleration cancel out. And mu is simply equal to sine alpha divided by cosine alpha. So mu is just equal to tangent alpha. What a beautifully simple result. It's really remarkable that that's the case. So if we zoom out just a little bit here, then it turns out that we can see that the mass doesn't matter. All objects will need the same minimum coefficient of static friction to remain stuck on this ramp. All that matters is the steepness of the ramp. That's really the only thing that affects how grippy or sticky the ramp needs to be. Small masses, large masses, enormous masses, they will all be able to stay stationary when released if there's enough grippiness, but that's it. It doesn't, you don't need more grippiness for heavier objects, is what I'm saying. All of them will either stick or all of them will slide. Put another way, suppose that we had a whole bunch of objects of different masses on the ramp when the ramp was horizontal. And then if we slowly start to increase the inclination of the ramp like this, all of them will all break free and start to slide at the same angle, the same ramp angle. And it'll be when the steepness of the angle approaches inverse tangent of mu. And that's it. All of a sudden, they'll all break free and they'll all start to slide at once. Let's briefly answer question B right here, which is, what does this become for the two limiting cases of alpha equals 0 degrees? Okay, so in other words, horizontal. Tangent of 0 degrees is just 0. So for a horizontal surface, how much grip do you need between the surface and the object for the object to remain at rest when you release it from rest? And the answer is none. You don't need any. That'll work even on a frictionless surface. If it's horizontal, you can release an object from rest and it'll stay at rest. And for a vertical surface, like a wall, okay, so for a vertical wall, how much grip do you need? Well, tangent of 90 degrees is infinity. If we approach from the 89 degree side, then it's positive infinity. So in other words, if you wanted to keep an object from sliding down a vertical wall when you release it, you would have to have infinite grip between the object and the wall. Put another way, you'd have to fasten the object to the wall with glue or a nail or something like that. Okay. All right, so that's example problems number 1 and number 4. Number 3, we basically did during the lecture already. And I'm going to recommend that you try questions numbers 2 and 5, which have numerical values, and they're more along the same lines here as question 1, for example. Well, one is without friction and the other is with friction. So you can try those for some additional practice. And then finally, in mastering physics, there's a small number of inclined plane problems in homework number 15.